So we know that all data, if we have a set of data, we can find the measures of central tendency. We can then, so that's the center of the data, the mean, the median, it's all different ways of describing the center. We know outliers will kind of shift our measures of central tendency, so they're really not quite in the middle. And then we know we can find the standard deviation and the mean. So remember, if you have a data set and you find the mean, the average, all of those data points are going to fall within some number of standard deviations away from the mean. So the more standard deviations out you have to go, the more spread out the data is. So if it takes 3 standard deviations to entrap the data, they're kind of spread out. So we know that you can find the mean of a data set, and then all of the data points fall within some number of standard deviations, right? Okay, so today we're going to be doing normal distribution, which is still dealing with mean and standard deviation, but it's called normal distribution, and that's when our data has a normal distribution. I'll explain in a second. So many common statistics in the real world, such as human height or blood pressure, gathered from samples in the real world, tend to have what's called a normal distribution about their average, about their mean. A normal distribution has data that vary randomly from the mean. So the mean is the average. The graph of the normal distribution is called a normal bell-shaped curve. So everybody look at this normal bell-shaped curve. So not all data is normally distributed. In fact, very few real-world situations have normally distributed data. However, if it is normally distributed, this is what happens. So you have your mean. So I'm going to draw my little red line here. You have your mean. And then 68% of the data, so 68% of the points, will fall within 1 standard deviation away from the mean. So that would be split evenly as well. So that would be 1 standard deviation above and 1 standard deviation below. So you see how 68 is cut into 34 and 34? So 34% of the data will fall 1 standard deviation above, and 34% will fall 1 standard deviation below. Now 95% of the data will fall within 2 standard deviations of the mean. So almost all of it. If 95% of the data, almost all of it will fall within at least 2 standard deviations. So grab your calculator, type in, we're going to do 95 minus 68. How much is left over? Because we already know this is 68, 27, and then it's divided by 2. So that means that leaves me right here, 13.5% will fall within this section, within 2 standard deviations above, and 13.5% will fall within 2 standard deviations below. You need to be like taking a screenshot of this in your head, because you have to draw this. You will see it on the ACTs. If I say it's normally distributed, these percents always work. It's always these same percents, so on the test you have to draw your own. So get these percents in your head. And then 99.7, almost all of the data will fall within at least 3 standard deviations of the mean. So we already know that 68 was here, and then 95 was from here to here. So let's do 99.7 minus 95. What's that? 4.7 and then divided by 2. So that means that 2.35% will fall within 3 standard deviations above, and 2.35% will fall within 3 standard deviations below. So then after that, look, barely any, so 0.3%, less than 1, will fall outside of 3 standard deviations from the mean. And so notice on your paper I said 4 standard deviations, but it's really just 3 and above. So maybe just draw yourself an arrow. I should have just said 3 and above, like fall above 3 standard deviations. Fall below 3, above 3 standard deviations. So then that's, if you take 0.3 and then divide it by 2, that's 0.15 and 0.15. So barely any, if at all any, will fall lower than 3 standard deviations from the mean. And these percents always work. Okay? Do you have questions? Memorize those percents. Okay. So I'll show you how, oh yeah. Like I said though, not all data is normally distributed. If it's normally distributed, it has a bell-shaped curve, and those percents always work. If it's not normally distributed, the mean will be skewed. Does that make sense? A little bit over, and we're not going to get into that, but I'm just making you understand that you can only use those percents if you know for sure it's normally distributed. Otherwise, more of the data falls over here from the mean, or more falls over here from the mean, if that makes sense. Okay, so I'm going to give you an example of how this works. So it says, For a population of male European eels, the mean body length and one standard deviation above and below is shown below. It's a normal curve, so we're told it's normally distributed at 1, 2, and 3 standard deviations from the mean. So I want you to look at these eels. So here's the mean body length, so 15.7 inches. So we would draw our bell-shaped curve. I spread it out to give myself plenty of room. Draw it as symmetric as possible. So our mean will be right down the middle here. So that would be 15.7 inches. And then it says one standard deviation above is shown. So then it will be up to 18.5 inches. That's one standard deviation above. And then one standard deviation below is 12.9. So now if you look at that and you add up that distance and you subtract that distance, it's 2.8. So our standard deviation is 2.8. Does that make sense? So then what percent goes here and here? 34% and 34% for normally distributed data. Does everybody understand? Okay, so then let's go to standard deviation. So take your calculator and do 18.5 plus 2.8 for me, please. Thank you. So 21.3 inches long. Interesting. Okay, 2.9 minus 2.8. 10.1 inches long. So then 13.5%. Getting these memorized, 13.5%. Let's do 3. So subtract that from that. Somebody else do this side, and then you'll shout them out to me. 7.3 inches long, that was 3 standard deviations, and it was 2.35%. Normally distributed data always has the percents I just showed you in the first. Always, good question. And then, sorry, good question though. Okay, what was this one? Okay, and then we don't need to do 4 because it's just beyond that, greater than that. So that's 3 standard deviations. So that's 2.35% will fall within that. And then 0.15% will be larger than 24.1 inches long. Barely any eels. Does that make sense? 0.15%. So, for example, now because we know it's normally distributed and we know this bell-shaped curve is true, what happens is, if I was to go grab 100 fish, okay, everybody, 100 eels out of the lake, we can literally, truly expect, if we start measuring these out, that 68% will fall within this measurement and this measurement. If I'm measuring them, 68 of those fish will be between that length and that length. Does that make sense? No, why did I say 68? Because I did 100. Does that make sense? Because that was out of 100 eels. So if it was out of 10 eels, we would expect 6.8, right? Does that make sense? So once again, if I said to you, how many eels can you expect to be between 10.1 inches in length and 18.5 inches in length? So isn't that this one, and this one? That's what we can expect, right? That much percent of those. So does everybody see how we do that? We'd add it up. So you would do, because if I said how many eels can you expect to be between 10.1 inches long and 18.5? So for 18.5 is here and below, right? Yeah, because 34% will fall in this length, 34% will fall within this length, and then 13.5% will fall within this length. So you just add them up. Does that make sense? Okay, awesome. So if I said to you, how many of these eels can we expect to be larger than 24.1 inches long? You would say? Good, 0.15%. Does everybody see how that works? So now if I gave you an exact number, so I'm going to go to this lake and pull out 200 eels. How do you spell eels? E-E-L-L-S? Or just one L? All right, let's just scribble that bad boy out. So I have 200 eels. How many can you expect to be in length? 7.3 inches long to, let's go with 15.7 inches long. So out of 200 eels, if this is our normal distribution, how many can we expect to be between that many inches long and that many inches long? So you'd add up that one, and that one, right? And then you would take that percent. What is that percent? 46? Oh, you might have typed it wrong on accident. Okay. Let's see again. Try that again. 34 plus 13.5. What was it? 49 point. Thanks. So 49.85%. So now to actually find how many ills, when you take 200 and times it by 0.4985, that's how you find that percent of 200. So you take 200 times 0.4985. How many ills? 99.7 ills. So we would probably say they always will use the word about 99 ills. Like this literally would be true. So if you went and grabbed 200 ills, you literally can expect about 99 of them to be in that length if you measure them out. It's kind of cool. Okay, awesome. Okay, so let's do one more example to make sure we're good, and that's all you have to know. It's that easy. So here we go. It says, the heights of adult American males are approximately normally, this is true, approximately normally distributed. So let's see where you're at, like what height you're at. If you know, then you'll see where you fall within the world. So let's look here, men out there. So the heights of adult American males, which although you guys aren't quite considered adults yet, so you probably will grow a little bit. So the heights of adult American males are approximately normally distributed with a mean of, I guess I should say you are adults, but you're growing still. A mean of this and a standard deviation of 2.5. Grab your calculators. Let's get going like maniacs here so we can hurry through this. So our mean is 69.5 inches. And then one standard deviation is it says 2.5 inches. So everybody start adding 2.5, add 2.5, give me these above. Let's just get this written out. Right here. 72 inches, okay. Okay. Perfect. So that was one standard deviation above, 2, 3, and then taller than 77 inches, and we'll just write that out. So 34% fall in here. In the real world, 13.5%, 2.35%, and then 0.15. So you would take your 69.5, subtract 2.5. Okay. Okay. 62 inches, and then lower than that. Barely any in the world actually fall lower than that. So let's see here. So 1, 2, 3, okay, 34%, 13.5%. So all of you boys out there, if you know that you're 5, like for example, I'm 5 feet 6 inches tall roughly, right? So I'd take 5 times 12, because there's 12 inches in a foot, and then I'd add 6 to that. So let's figure out, some of you, I'm going to ask you men out there, how many inches you are, and I'm going to just see where you fall because I'm interested. So how tall are you? You're 71, so you fall within one standard deviation from the mean. So you're a little bit above average, so that's kind of interesting there. So anyways, cool. A little bit above average, but you're definitely not in the, you're not obscenely tall. Okay, awesome. How about you, Corey? 72.1, so he's a little bit, 72.1, so you're actually kind of rare. Your height is kind of rare. Only 13.5% of men in the world really are about that height. Does everybody see how that works? Cool. So then you can kind of see where you're at. Okay, awesome. So I was just curious, fun to do. All right, so are you guys good with those? Hey, what you're going to do is skip 1 through 4. We're not going to do those. Skip 1 through 4, but the rest of that you should be able to do for the most part. Skip. So ready, set, go. Start drawing out normal distributions. I want those percents in there every time because you got to get them memorized. Hurry and post.